Okay, so we are running a little late today because I forgot my camera to my university office. So Mustafa is currently picking that up, and here we have. So we're gonna have a camera connected momentarily. Uh, what else we need? Okay, so this one I need to connect another end to my computer. Okay, and then what? To get the camera video capture device. Do we have that? Is that a Dell?
Yes, yours.
I mean, it's a Dell. Is it?
Yes.
Why it's still not showing anything? So it's HP. Is me. I want to use the Dell. Okay, looking good. Looking good. Chroma key is missing. So how come it disappeared? No, no, I think it is there.
Okay. Where do you want to stand?
Okay, so it's gonna be like somewhere here.
Is everything okay?
Do you think that I got like some kind of like a medical condition or what? No. Okay, so it's good. Put it a little bit more up. A little bit more up. Bit more. Yeah, that's perfect. That's perfect. Okay, so we are good to go. Except this guy is
Let me
not.
check the voice.
I see that the voice goes out. I see that much. And then okay. Still not. You don't hear me or? Yeah, it's okay. So it's okay.
Okay.
So it's okay. So is it? But this is why is this is not still willing to display anything? Okay, so let me see. Do I have my display? Can you see if there's anything coming off when I do like this? Oh yeah. I'm wondering why it is not displaying anything. Sometimes it makes a big difference if the cable is not connected. Not always, but sometimes. Okay, so how it look? I need to take myself completely another location. Why the heck this projector is not doing anything?
On.
It is on.
This one.
All right. All right. Okay. I think we're good to go. Yep, we're good to go. I see we 3 minutes, 3 minutes behind the schedule. Okay, guys, you ready? Respect, respect. Lecture number 10. Lecture number 10. This is going to be the last lecture about the hydraulics. How is the voice quality? Is it okay? So everything is good. Okay, so we do have somebody that is checking out what are the online participants are saying, who would like to be a YouTube officer at this time. Okay, no comments from online participants, I hope. Okay, all right. Okay, so this is going to be the last lecture about hydraulics. Maybe we'll see how fast we're going to be today, but if everything goes as planned, we are able to cover a few of the components. The components we are planning to cover today is a throttle valve, just to warm up, just so you could get an idea how is that the components can be modeled. And then the real deal will be the direction valve, and then the pressure relief valve will be your reading assignment, cylinder and the pump. Those will be the components we're gonna discuss today. And if everything goes like I'm planning, we have a very extensive example as a end of this series of hydraulics, and then we're gonna move on to completely different topics. You see here is a little bit unclear what are the reminding topics because last week I mentioned about flexible multi-body dynamics and real-time simulation. Now I'm saying is artificial intelligence and mechanical engineering. Still, I'm a little bit thinking like, what is the way that I can make you to be astonished? What are the subject matters that will be the most beneficial to you? But one thing that will happen, and that I figured is going to be lecture number 13, that's going to be the recap and party. Recap and party. And the party will be such that, remember a few weeks back, more than a month ago, I said that if you guys are scoring 100%, I'm going to give you the coffee. But I think that was my promise, right? So now I need to make that to happen. So it's going to be the last lecture that you're going to get the coffee service in this lecture. Or we can go and have a coffee in a cafeteria. We'll see. But that's going to be the last thing to do. But before that, it's going to be recap. And one more thing we discussed a week ago was carrier counseling. This is not going to be the core material anymore, but it's something that I feel that is important me to keep my thoughts about the carrier counseling. What makes sense to do in terms of carrier counseling? What is it you should avoid to do as much as you can? And what are my tips to you? And that's going to be really the last lecture, but nothing to do with this course anymore. This is like extra material. So that's going to be after we have the party, carrier counseling. And those of you that are not you don't care to listen about the carrier counseling, fine. You just simply skip it. Okay, so modeling of hydraulics, that's what we're going to do today. Good. And let's get started by usual way. So let's summarize what we discussed a week ago. So a week ago, we were able to derive the first order differential equation that tells how is a pressure at any given time. And this was a result of a method that was called lump fluid theory. And as the title already implies, so it's lumped. So we're considering the points in a hydraulic circuit where we are assuming the pressure to be equally distributed. This is a kind of like a discretization procedure, which is pretty straightforward. You can see clearly that there are components that are introduced in the pressure losses. And if there's a pressure loss, of course, we cannot make an assumption that, if because of the pressure loss, the pressure is same in two different containers. If there's a pressure loss, we need to use a multiple first order differential equations to compute the pressure at any given time. So what you do is that you're discretizing your hydraulic circuit within the volumes where you are assuming pressure to be equally distributed. Then what happens after that is that you're using this equation to describe the pressure as a function of time. And by the way, it's very, very important, extremely important before you do this, while you do the discretization, that you're also describing what is a positive direction of the flow. And you can do this anywhere you want, but something that is extremely complicated and hard to do is to be consistent. And the way that you can be consistent is that you have this physical description, what you think is kind of the positive direction. But like I said, you can describe the positive direction any way you want, but you need to define which one is incoming, which one is outgoing. All right? Flow rate. All right, the components that I have in this equation is effective bulk modulus, the one that is describing the flexibility of fluid. Volume size, physical dimension of the volume. Then there's a flow rate in. And again, which one is in, which is out. This is something that you can decide at however you want. The only thing that matters is that you just need to be consistent. Okay? This is in, this is out. And in a certain components, there may be a chance that the volume itself is changing as a function of time. Hydraulic cylinder is a good example. So that's the third component. So that's a differential equation that computes the pressure for any given time. This differential equation is a little bit problematic because it can lead to situation that it predicts the pressure to be highly negative, like cavitation. Cavitation can happen in reality, but it's more a complicated phenomenon than this equation implies. Usually this equation is made in a way that you're monitoring what is the actual pressure value. And if the pressure value, so let me make a drawing here. So if there is a, for example, case like this is a pressure, this is a time, and if the pressure is dropping heavily like this, it becomes to be below a certain threshold value. Threshold value could be, let's say, a 1 bar, so atmosphere pressure, so 1 bar. There is an algorithm that recognizes, okay, we're going down and we're going down fast. And then if this one here, which is a P dot, if P dot is a negative, meaning that then this tangent here is having the slope that is negative like this. So it means that you're really going down, and it seems that you're going all the way to negative part of the pressure, which could be the, I mean, in reality it would be the cavitation. But as a cavitation is more complicated than that this equation implies, what is usually meant in this case, or what is usually a procedure in this case, is that you simply take this pressure, this a negative pressure, you say that, okay, this negative pressure, you're forcing that to be equal to 0. So then it levels off. So then it's like, as soon as it goes below the threshold, it's kind of like keeps its value here. And as soon as there's going to be more flow coming in, then it bounces back from the low pressure side. So that's the trick. That is, most of the software is available, not all, but most of the software is using this kind of the symbol trick. All right, example about this discretization is this. So here is a damper, a fluid damper, and as I cannot assume that the pressure upper part is the same than the lower part, I need to compute the pressure in both of these volumes. So how do I do that? Well, I first of all create the effective bulk modulus that is describing this fluid here. I'm going to take the volume size into account. I'm going to take the flow rate in. And now really what matters, how you're going to describe the positive flow rate. If you say that the positive is this one, then what is actually coming in is nothing. But what is going out is going to be this one. And then, how you're going to describe, this is going to be how the volume itself is going to change. And then here, I have the same equation, but I have different parameters. Now I have effective bulk modulus that is describing the fluid in a lower part of the damper. And then I have the volume size itself. And now this one here is the one that is coming in. You see here is a positive direction. So this one is coming in. This is nothing. So nothing is going out. And then this one is the one that is describing the volume size. Okay, right. Here's another example about discretization. So very good example, because now you see that I have my assumption about what is a positive direction of the flow. Let's look at the one example. So let's look at this one here, the P1. How can I compute the pressure in this particular volume when I make an assumption about the positive flows like this? All right, so it's going to be like this. P dot is going to be effective bulk modulus divided by volume size. And this is a hose or pipeline. So this is somewhat easy to describe the size itself. And then what's going to be the flow in? So this one, as the arrow points it out, that's coming in, is my incoming flow rate. And let me emphasize, it's extremely important you to do these drawings, because you might think that I have such a big brain that I can memorize how is a positive direction. It's not going to work out. And you make one simple mistakes in your flow directions, and your hydraulics always go crazy. So it makes no sense whatsoever, and it takes your hour in, hour out, day in, day out, week in, week out. You still can't figure out what is wrong in your hydraulic circuit. So please be as careful as you can. Okay, so what's incoming? This is incoming. Correct. Okay, so this needs to be here. So it's a QA1. So that is incoming. What is leaving? This one. This is leaving. This is going to be minus QA2. What is this component? How much is this component? This third component, the volume size, change as a function of time. Do we have it or not? What do you guys say? So it's simple. Who is voting yes? So we have the component. Who is saying we have the component? Who is saying no? Okay, so you guys are very neutral, so you don't want to vote at all because you don't cast a vote. So what if you have to if you are forced to cast a vote? Which one are you gonna select? Yes or no? This is not gonna affect your grading, your life. So you can do this freely. So which one do you select? Do we have this component or not? No, you guys are voting this one. And you are correct. We don't have this component because there's nothing in this particular pipeline that is changing the volume size because it's a pipe. Pipe is not getting shorter or longer. It's having its volume as a constant parameter. Okay? That's very, very important to understand. Here in a P2, that's not the case. Why not? Because a piston can travel up and down, so back and forth. And when the piston is traveling up and down, the volume size is actually changing. And it is corresponding the volume in or volume out. However, you define it positive direction again. Again, you need to be consistent. If you think that the positive piston movement is this direction, when the piston is moving positive direction, when the piston is moving upwards, it is kind of taking the volume off from this P2, whereas it's pushing flow rate to P3. So again, doesn't matter how you're selecting the positive direction, but please be consistent with that. Okay, that is my message. Let's practice. Okay, here is a simple hydraulic circuit where we assume that there's a flow rate that is coming in, and it is Q described here. And then we have here a volume, which is actually defined in a way that there's a certain position where the piston is traveling, and there's a cross-section area of the piston. This is a one-way cylinder, so there's no pressure in a piston rod side, nothing in this side. Okay, how is it we can compute the pressure that is in below the piston? So again, we're going to make a use of this equation. So let me rewrite it. So it's a P dot. It's going to be effective bulk modulus divided by volume size. Then it's going to be volume flow rate in, flow rate out, and then it's going to be this component that is describing how much the change of the volume is going to make a difference. This one here, how much is leaving, is nothing, because we have only assuming that the flow is coming in and it's assumed to be positive. It's possible that it is the flow rate is against, but this is something that will be automatically accounted if you make these plus and minus to be correct. Okay, so this flows goes here. We have to compute the effective bulk modulus. We have to compute the volume size. We need to compute how much the volume is changing as a function of time. Great. So those are the components we need. So let's get started by first defining the volume size itself. That's going to be simple because there's a hose line, this one, that is connected to this cylinder. All right? Cylinder volume is going to be, there's a cross-section of the piston multiplied by wherever the piston is traveling. So with respect to coordinate x is defining how much is the stroke where the piston is traveling. Okay? So that's going to be your volume. And then effective bulk modulus is something we practiced to use a couple of weeks back. So it consists of this time 3 components. So there's a flexibility of the fluid itself, flexibility of my cylinder component, flexibility of my hose component, and the corresponding cross volume areas of the cylinder and the hose. And the one that is here below is a total volume. So it's actually the one that is computed here. You did all the substitutions, and the effective bulk modulus can be written like this. And when you do all the math, it's not showing clearly. Here it is. This is already effective bulk modulus. I'm sorry about that. So sorry for being unclear. So effective bulk modulus can be written like this. Okay, this guy, change of the volume is, of course, it's going to be the cross-section area multiplied by piston velocity. So it's this x and x dot. And again, I have my positive assumptions like shown in the figure. So what I need to do as a final thing is my substitution. This is effective bulk modulus. This is going to be the one when I compare the total volume size. Flow rate in was this guy here, was substituted here, positive in sign. And then the one that is taking away the flow rate is going to be the piston traveling this direction with a certain positive velocity. What do you guys think? Makes sense? Makes awful lot of sense. Or none of this stuff makes any sense. The course doesn't make any sense.
Explain the last one.
This one.
Yeah.
This one. This I think it is
P dot whole thing. P dot.
a p dot.
Yeah, yeah.
Okay, one more time.
Yeah.
Okay, from the beginning.
Yeah.
Okay, we have a particle. And we have the Big Bang. And what came out from the Big Bang was a particle. You want to get started from this far off, or should I come a bit closer? Okay, a little bit closer. Okay, the p dot. Let's get started here. You know, remember this. So what we're doing here is that we're computing not pressure, but the pressure change as a function of time. So that's what we are defining here. So this is a tangent of, if you have, for example, the pressure curve, like pressure, time, and it fluctuates like this. This is all the time the tangent of this curve. That's what we're predicting here. So we're predicting the change of the pressure. Not pressure itself, but the change of the pressure. How we can get the pressure itself from the p dot? By using integration procedure, time integration procedure, because this shows the p as a function of time. When we are, integrating the p dot, we get this one. That's what happens. How we can do this thing? So we can do this thing by using the equation where we have the effective bulk modulus divided by volume size. Then we have here how much flow is coming in, how much flow is leaving, and how is change of the volume itself. Those are the components. So these are the kind of defining is it going to be positive or negative? This is kind of the define the kind of like how is angle of this tangent component. So a little bit of like how stiff it is. That's what this is defining. Okay, now what I did here was that I first compute the effective bulk modulus by assuming that it consists of three components. These three components are flexibility of fluid, makes sense? Flexibility of the steel container, which is the container made out of steel, okay? And then this, by the way, you need to compute using the equation that I described last week. So there is a simple equation how to do that. And then the last one is how is the flexibility of the hose component, how much the hose itself is deforming, all right? Now I have my three components, and these three components are defining my effective bulk modulus, the one that is describing all the flexibility that is coming out from the hydraulics. When I do my math, when I'm solving the effective bulk modulus, it can be expressed like this. Where did I got this? How was I able to do this complicated math? I wasn't. I use a symbolic math tool, and it gives me automatically. I say, here's my equation, solve me this guy. And he's able to do it. Okay? And I recommend you to do the same. Then it continues. Then is this last component that defines that this, if the p dot is positive or negative, is how is change of the volume itself. Change of the volume is something that you need to consider carefully, because it is actually coming from the cross section of the piston multiplied by velocity. And now if velocity is this direction, positive velocity direction, it is kind of taking the flow rate off from this particular area because it's kind of sucking the flow, sucking the material off. And that's why it's going to be negative inside. It's going to be negative here. So the rest is simple substitution assignment. Here's my effective bulk modulus, this one. Here's my volume size, this one. Here's my flow rating, this one. And this is my change of the volume. What do you guys say? It's okay. Makes sense? Okay. Again, maybe I did not mention this too earlier, but it's very important to be consistent. Because I have seen people to lose their mental health because they don't do this drawing. They simply assume that, yeah, I remember that this is the positive direction all the time. Yeah, they remember like 2 minutes and then it's off from their head. And they started to create these differential equations needed, and they make an awful lot of mistakes about plus and minuses. And if you think that the flow rate is leaving, but it's actually coming to your flow, you can understand the consequences. The pressure is behaving completely incorrectly, like absolutely incorrectly. You can get the pressure values that makes absolutely no sense. So lesson learned, make a drawing, be consistent. Okay? Makes sense. What is this? Is this again, was it again like interaction between you and me? Was it? It was. It was. It's all recorded, so I can get back to this. If I feel bad any of one of these days, I can go back and forth and look when there was a nice conversation between you guys. Any other comments, questions? Clear? This makes sense. Okay? This needs to make sense because, like mentioned, there are a lot of these tools that you can model the hydraulics automatically. You could just take a component, put it in your screen, explain the parameters, connect your component to another component by hose lines or pipelines. This is what you can do in a real life. But once you model this by using equations, which is what you're going to do, you need to be very, very careful. But it's doable, definitely. But if you're facing any difficulties, please ask help from Surats and Mustabatser. Okay. Okay, let's look at the few components. Let's look at the first throttle valve, and then we're going to move on to real body of today's lecture, which is directional valve. And then we're going to look at the cylinder and the pump, pressure relief valve, which is not going to be very important for us. I mean, it's a very commonly used component, but in this class, we are not going to spend much of the time for that because it's going to be like one of those components that are pretty complicated to model. Needs a lot of parameters to obtain, so we are not going to touch that in details. But we do touch the throttle valve and direction valve in details as we're going to do for cylinder and a pump. Okay. Throttle valve. First of all, there are 3 different ways how the modeling can be conducted. The modeling of components, which is what we are currently looking at, can be conducted in 3 different ways. You can do this completely analytically. It means that you take each of the components and you describe them as they are in the physical life. And when you do that for a throttle valve, it's going to look like this. It's going to be equation that describe, first of all, the discharge coefficient. This is something that those of you that have studied the hydraulics, it is clear, like how much it is actually resisting the flow, or how much it is actually introducing the pressure differences. Then there's a physical diameter of the throttle itself, and then it's going to be density of the fluid, and then under the square root is going to be the pressure difference. So pressure difference is under the square root. It means that the flow rate as a pressure difference is quadratically related. So the assumption that I'm using here is a turbulent flow. So you can model this as it is shown in this equation, explaining everything analytically, which is okay, but it's difficult. And it's difficult because most of the components you use in a hydraulics are way more complicated than a throttle valve. Just to give you an example, pressure relief valve is going to be the something that, there's a spool that is moving because of the several different forces. There's a flow roll force, there's a pressure that is imposed to the spool, there is a spring force, and so on and so forth. To create the equation for the spool movement is going to be a painful task if you're planning to do that in details based on physics. Possible, but very complicated. That's why there's an alternative. An alternative is the one that is based on just measurements. You do nothing but measuring different components. And then you can defining like component, how it behaves under this different kind of configurations. How it behaves in a different pressure values, how it behaves when the spool position is this and that, how it behaves when the pressure, the spring initial pressure, initial force is this and that. You're creating the kind of the library, which you can call as a lookup table. Lookup table is that these are all the possible input parameters, and the behavior is corresponding like this. This is something that is called empirical approach. So we have two choices. One that is based on fully equations and analytical approach. Another one that is fully based on measurements. The one that is turn out to be the best is the one that is here in the middle. And the here in the middle works like this. You get started in your modeling by using analytical equations, but then you're moving or you're manipulating these analytical equations in a way that they are expressed in a way that you can get these parameters from simple measurements. Simple measurements that are typically offered by manufacturer's catalog. So the measurements you need to do by yourself is nothing. You just take a look at the components. This is the component that I like a lot. This I think it is going to work well in my hydraulic circuit. And then you look at the manufacturer's catalog. What are the parameters? What are the characteristic curves? Based on this information, you're able to create equation that is describing for your particular equation. What it means in the case of throttle valve, it means this. These parameters that are seemingly simple to get, like diameter of the throttle, it might be hard to get it in real life, but you can get something that is characteristic curve. You can see how it is behaving as a function of the pressure difference. And based on that, you can see if it is a turbulent or laminar flow. Most probably it's going to be a turbulent flow. And then you can just take all these parameters that are separated from the pressure difference and express those by using one single parameter that is called semi-empirical parameter. Parameter that is here called CV, semi-empirical parameter. How much information we're losing here? Nothing. Because you see that if you're going to substitute this one here, it's going to be exactly the one we're looking for when we made this analytical equation. Why we do this? Because now we have a clear relation between the pressure difference and the flow rate. And this is exactly what is typically offered by manufacturer's catalog. I understand that you are not getting excited yet, because this is such a simple component. Such a simple component that it doesn't really is not that much of work to model this, even when defining this throttle diameter. Yes, it is possible, but this becomes to be extremely handy when we look in the components more complicated than the one that is a throttle valve. Okay, I mentioned this a week ago. The one that is a man behind of this technique is a man that you know. He's a professor at one of the best universities in this planet. One of the best universities in this planet is this. How you guys like about this marketing statement? Okay, so his name is Heikki Handru. So Heikki is the one that created this when he was a doctoral student a couple of years back. Okay, anyway, so he's been developing this for many other components, and you're going to find this to be very handy. Okay, here's an example. This is a typical thing you can get from the manufacturer's catalog. This is something that is called characteristic curve. And they're offering these curves, characteristic curves for many different kind of components. All right, let's just think that hypothetically you wanted to get the throttle valve. If you look at the manufacturer's catalog, and it's offering you a curve like this. This is the one that I can offer to you, how much you like about it. And now you wanted to model to figure out if you really like this or not. Okay, what you need to take a look at this in the very beginning. First thing is that you need to understand that because this is a pressure difference and the flow rate. The first thing that you need to observe that this curve is quadratic. It's not the linear curve, but it's a quadratic curve. That means that the flow that you're dealing with is going to be turbulent flow. So the pressure difference is going to be under the square root. That's for a fact. And then the next thing that you can figure out that, okay, what about the rest of the parameters? Because there's still something missing here. The flow rate is equal, then the question mark, and then square root under the pressure difference. Then what is the missing component? That is the one that you can get from this characteristic curve. How? You simply take any point you want from this curve and you substitute the values. Here I select this point here. You substitute the values to this equation. Here is going to be the flow. Here's going to be the corresponding pressure difference. And of course, the thing you need to do here is that you need to convert the values to be SI units. Okay? So what was the first thing to do was the flow rate, and it was expressed in liters per minute. Not good. Not good, because that's not the SI units. So let's convert that to be SI units by dividing by 60,000. Okay? And that's, when you do that, that's going to be the one that is going to be this part of the equation. Look at this one, and this one is all the time same stuff. Then the pressure difference, again, this is not good because it's given by bars. You want to express that by using SI units. So you need to take 100 multiplied by 10 power 5, and it's going to be in the SI units. When you do this, this is going to be your semi-empirical parameter. Look at this. Lesson we need to learn from this is that the units is quite complicated because it's a square meter divided by seconds divided by square root of the pressure. So it's quite complicated units. And of course, you can kind of play with any units you want, but here's another important lesson when you're modeling the hydraulics. Stay with the SI units. And don't convert them to be millimeters, but stay with the meters, even though that sometimes you end up to have a very small or big numbers, but it really helps you a lot because conversion from these units to something else is possible, but again, you need to be consistent. Another component is it can be mission practically impossible. Okay, so that was the first component. So let's look at how is an equation itself. This is how the equation look like. So I have here the flow. Again, I'm making an assumption what is a positive flow rate direction. Is it this meaning that I cannot take the flow in opposite direction into account? No, I can still take that into account the way I model the component. And I model the component in such the way that I have first here this semi-empirical parameter, the one that I got from the characteristic curve. And then comes the sine component, which I'm going to explain to you momentarily. And then I have here a square root of the pressure difference. Here's a pressure 1, pressure 2. And I'm going to take a determinant here. Why? Because if I end up to have a negative values under my square rule, I'm going to have a major problems in my life. And I want to make my life to be enjoyable, so I don't want that to happen. So that's why I take a determinant here to forcing this component under the square root to always to be positive. But wait a minute. I just say that the flow can travel pleasure. The flow can travel this direction too. How can I take that into account? I can take that into account by using the sine function. Sine function is something that can have 3 components. I'm going to put it like x here. It can have 3 scenarios. It can have 1 if x is having the positive value. It can have 1 when x is having 0, and it's going to be -1 when x is less than 0. I said this incorrect. X is equal to 0. So these are the two components. So it's either 1 or minus 1. Those are the two choices that this function can give it to you. So what it's doing for you is actually changing the order of the flow. So it can go this direction if this pressure is higher than this one, and opposite direction if it is other way around. Makes sense? Makes sense. Okay, then let's move on to real component that is going to, like mentioned, this is where we're going to spend a little bit of time. Okay, now this is something that we need to have a completely different point of view, because now it's no longer about the single simple parameter, but now we have a component that there is a moving body. And when the body is moving, first thing we need to do is that we need to figure out what is actually the spool position, where the spool is located. For example, this one here, this is a pressure relief valve. If I do not know what is let me see how can I measure the spool position. It is measured here. So this is my X. This is my X component. How far the spool is moved from the place where the valve is fully closed. You understand that flow rate depends heavily on the spool position, because if it is just a little bit of opening, then it is limiting the flow quite significantly. Whereas if it is fully open, the flow can travel almost without any significant resistance whatsoever. So I need to know where the spool is located. So the first thing, where's the spool? Then once let's say if it is not the spool, it can be a poppet. I still need to know where that is located at. And once I have that information as a function of time, then I can move on to my next phase of the modeling, which is how much the flow is traveling through the component. It's like, remember in a previous example, it was like the CV, which is a function of time. The CV is no longer constant value, but it can change as a function of time. Then that is then under the square root of pressure difference. This is what CV. This one here is actually describing the spool position, where the spool is traveling. Okay, makes sense. Then once I know that, then it becomes to be simple, because then I know how much flow is traveling through my component. How much the flow is trying to equalize the pressure difference, which is this guy here. What? You say yes. Okay, I'm looking your face. You're still alive. Everything is going well. Okay? Very good. So we can continue then. Very good. Very good. Let's continue then. Okay. There could be, million different kinds of valves. And, even the direction valves, there's a lot of different varieties. And we're going to look at just the simple ones. Usually they can be operated, the modern valves, of course, are operated by magnets. So there is no physical connection from the operator to spool itself. Let me correct that. This could be the like low quality ones, like if you have like simple on-off system, or let's say the simple one of these small tractors that you might have in your farm. I don't know if you guys have a farm. You might have a valve like this one. Like there's a mechanical connection from like a stick that moves the spool back and forth. But in a real, like something that is a commercial products, high-end products, is hard to find anything like that. But anyways, so here's a good example about the direction valve where there is a spool that is moving back and forth. You see that this the symbol for this kind of the valve is this. So it's having the three operation configurations. The one that this P is connected to A, this tank is connected to B. They could be fully closed as they are in the middle, or they can be connected the other way around. So those are the choices. So how it goes? It goes like this. So here in the middle, they don't move anywhere at all. So there, this configuration correspond this drawing symbol. When I push this stick to the left, this spool is moving, and then the P is connected to A. So this is corresponding this configuration. This here is corresponding this configuration. Now, in a modern machine, same, but no physical connection. So there is typically a small joystick. Joystick sends the signal to the controlling scheme, and the controlling scheme is moving the spool back and forth. Concept is not any different than this, except no mechanical connection. Let me show you this. So I'm going to show you something that I'm going to jump a little bit to my presentation, and then I'm going to be back where I was. So I have here two different kind of this one. So I have here two forest tractors, lock loaders. The one that is a Ponce Elephant King, and another one that is a Valmet. Um, which one is corresponding my childhood? When I was a child, which one was more in the fashion? Correct, Ponce Elephant King. Okay, so they look like, if you look at the mechanical structure, yes, there's a little different, but the operation principle is not that much of a different. Still, we have a like diesel engine that is rotating the pump, that is then actuating the cylinders here. But there's a major difference when you look at inside the cappings. This is how the capping looked a little while ago. You see that there is a mechanical connections from the shaft is connected to direction valves. Here, it's connected, but not mechanically. There's joysticks, and the joystick can help you with certain decisions that you can make. You can automate this. You can make this to be more pleasant. This one was how things were a little while ago, but the operation principle is still pretty much the same. This is what I mentioned a week ago too, and I said that there's a big promise that is hoping to change the concept of hydraulics, because this hydraulics was based on the pressure losses, as is the case of this too. Okay, so extreme statement, because yes, I understand that there are pump technology here that is more advanced than it was here, but still quite a bit of pressure losses. Pressure losses is energy losses as well. So what can be done in that regard is digital hydraulics. Okay, now I'm going to take myself back to the direction valves, but as I see that is 5 minutes past 5 o'clock, so we're going to have a break. How much we need? 10 minutes or how much? 10 minutes. And then we're going to continue with the direction valves, and then we're going to discuss about hydraulics, and we're going to discuss about stick slip friction, and we're going to discuss about digital hydraulics particularly. Okay. Yeah, as I learned a week ago, you guys are not aware of the digital hydraulics, so you need to learn that. Have you heard about the stick slip friction? Okay, another thing you can learn once you come back. But before that, go and take it easy and come back in 10 minutes. I see. I see. Yeah. All right. Very good. Very good. So it's going to be a few more slides and then my first in-class quiz of the day. It's been a while, no in-class quizzes. Because I think I need to call my wife, like, can I have it more? Because it becomes to be so expensive that, and she said, yeah, I can still have some, but I need to go down with my promises. So that's what I'm doing then. Okay. So I think we pretty much, a little more and then we go again. How is your Christmas exam week? Is it gonna be 1 week or 2 weeks that you have your final exams? Just before the Christmas break. So is it gonna be looking bad or is it okay? It's okay. Okay. So what is the exam that you're most scared of? None? Look at that attitude. Welding exam is the worst. Almost theoretical. What is this? What is that we do? So where you can see the practicalities, what we do is that this is super theoretical too, isn't it? Ah, okay. Okay. So what is in a welding then? Okay. All right. So let me take myself back. So who can take it out? Take a look at that. There is displaying well because sometimes when we get started after break, um, it's not. It's showing the black screen. So is it? Hold on. Is it okay? So can somebody take a look how is YouTube is looking good? It's looking perfect. Okay. Because this was something that for some reason when we have a break and when we're coming back, it's showing just the black. And I cannot see the comments from online participants. Okay. Do we have any comments from online participants? No. Hopefully they're still alive. We're going to figure out that momentarily once we have our first in-class quiz. Okay, so we'll learn that positive feedback. Okay, thanks God they're not here because I have this tendency to hug people. Okay, and this person is no longer living the LUT. Is that correct? Okay, yeah. So sudden change of heart, not leaving you. Oh no, no, oh no, no. You must leave. You still need to get your degree. You still need to leave. You can stay if you get your degree. Okay. All right. Here I have a direction valve. Again, I have my spool, and then you know you see that the drillings are made in the way that you can see here. This, the one that is a white in a color, I hope that this is displaying well. This is the one that is a spool. And this is a land that is blocking the flow. And it is exactly, the land is exactly the same size that the drilling. So it's just blocking the flow. So which out of these drawing symbols is the one that is describing this particular valve? Again, this valve, the spool of the valve can be operated by a stick. It can be operated by magnet. It doesn't really matter how you do it, but this is how they look. But which one is the drawing symbol that represents this particular valve? And also I need to correct when I said that, when we look at this Valmet forest structure and the Ponce, that there is no difference in the hydraulics. Don't get me wrong. Yeah, of course, there's hydraulics is involving, and there, of course, the direction valves are, having the better capabilities than what they were a little while. But still, like the basic operation principle have not changed that much. That's the message I wanted to give it to you. Okay, but which one is correct? So we have here A, B, and C. Which one is correct? So what do you guys say? This is something that you can vote freely. It's not going to change your life, but just to make sure that we're on the same page, who is voting for A? Hands up. Me. There's only me. Who is voting for B? Team Finland. So it's only Team Finland that is voting for B. So rest C. Winner today is Team Finland. Why? Because look at this, like I said, the land is just in the size of the drillings. So it's just blocking the traveling of the flow. So it is the one that this middle operation is this one. This is not what we have here because in the middle you can plug the view, you can plug the flow rate. Okay, how you can construct the land? You can construct the land that is not blocking the flow even when it is in a middle position. There is still a certain amount, even, by the way, even here, typically there is a certain amount of leakages. So it's hard to calibrate your spool in a way that there's no flow whatsoever when you have this zero land system. And you can have even the minus land, like it is shown here. In the middle configuration, everything is connected. More or less everything is connected. You can have this zero land, like the one we looked a little while ago, or you can have the positive land. And the positive land, the same drawing symbol than in a zero land. So no difference. But there's a clear difference in terms of operation. Because once you have a land bigger than the drillings itself, you need to move the spool a little while to make any kind of flow whatsoever. And it behaves like this. This is here the curves that is showing the valve opening, meaning like how much I'm moving my spool back and forth, and how much is the flow rate. That this is a theoretical representation here. So if you have here a zero land, depending how you do the drillings, it can have these linear relations, that the flow rate in the same pressure difference is linearly related. They can be proportional. The proportional means that this curve is having the linear path like the one that is showing this one. This is used in a certain application where you need to have very accurate positioning, and also you need to have very fast max speed. So if you want to really position something accurately, this is this one. When the motion is very minimum, when you want to have a full speed, it's going to be this one. So this is a combination of accuracy, max speed. And it could be the one that is like that we look at here, this one. There is nothing happening here when you're moving the spool, and then it started to open like slowly like this. So this is a proportional quick opening. So if you really want to put all the speed on in the very beginning, and the linear. So each of these are possible depending how you're configuring your spool position. The spool configuration. Back to the modeling. How we do the modeling of hydraulics. First step is this. We need to know where the spool is located. Most common spools and the valves that are currently used are the ones that are magnetically operated. So it goes like when we look at these forest structures, you have this joystick. A joystick sends a signal to magnets. A magnet is moving the spool correspondingly. So actual motion is conducted by magnets. The magnets that are quite rapidly moving this spool, the spool is actually a little longer, moving is back and forth. How we can model something like this? Typically it's modeled by using a first order delay equation. Delay equation means that even if there is a signal that is step signal like this, let's say that the U is a spool position, and you have first, signal, this is a voltage that is coming in, voltage is 0, and then all of a sudden it jumps to max opening. Because of the inertia, because of the physical component of the spool, even when you have a lot of forces here from the magnet, it follows with a certain delay. And this delay can be described by using first order delay equation. Okay, so what is that I have in my delay equation and how it behaves? It behaves like this. So if I make another look at about this step, So the step goes like this. And because of the inertia, because of the not that much force is in my magnet, the actual spool position will follow it with a certain delay. This delay is described by this time constant. How you can get this time constant? Because it varies from one direction valve to another. This is what you can find from manufacturer's catalog. And I will show you how you can make it happen. Rest of the components this is an input signal. This is what is coming from the joystick. Or if not, the joystick is coming from the control scheme. And it might have this kind of the step function that is saying, yeah, I want to have a full opening like right now. Move as fast as you can. And fast as you can will be with this certain delay. That is how it's actually moving. Okay, so this equation is not exactly the spool position, but it's a differential equation that tells you, let's say, that gives you the opportunity to solve the spool position. How? Because I have here the U dot, which is representing the spool position. This equation describes spool position. Spool position. Guess what's going to be the first in class quiz? Okay, so it's describing where the spool is traveling as a function of time. And actually, look at this. So it's a U dot. So you need to, of course, solve the U to figure out what is its actual absolute value, how much it is open or closed. Okay, that's how it goes. So what about this time constant, the one that is showing how fast you can react to changes, rapid changes? This one. This one you can get from the border diagram that is typically offered by manufacturer's catalog. Border diagram we're going to take a look at momentarily, but you simply you look at how far, what's the frequency that the difference between the actual signal and the spool position becomes to be more than 45 angles. You understand nothing about what I just mentioned, but I will show you an example, and it all becomes to be clear to you. So you're going to take a look at this number. You substitute that to this equation. That's going to give you this time constant that is describing how fast is your valve. Okay? My equation will be this. My float will be described as a function of the square root of the pressure difference. Here's my pressure difference. I have my semi-empirical parameter that is describing how large, what's the size of my direction valve, and where is the spool position. U here is describing wherever is the spool located at. If it is fully opening, you understand that the flow rate will be pretty big, whereas if this is fully closed, if this is a zero, nothing travels through this component. So this is how I do that. We are not yet in a phase that we can exactly express the equation, but we become to be close of it. But you understand the concept. Okay, let me ask you this. Physical interpretation of this equation. This equation, which is a U dot, U in, which is a control signal in, U time constant. Is it going to be the pressure drop to the valve? Is it going to be flow through valve, spool position, number of ports in a valve? One only is correct. And in-class quiz is on. How is it going to be today? How are we going to score today? So what do you guys think is going to be the success rate? Because many of them make sense. We have discussed about the pressure losses. We have described quite a bit about the flow rate. We have discussed quite a bit about the spool position. We have discussed about the number of ports. But one only is correct. Which one is correct? What is that the WhatsApp community is saying? So WhatsApp community is voting for C. Interesting. C. Okay. Okay. Let's take a look. I need to see this because there is a critical number, and the critical number is, of course, How many? Oh, yeah, yeah, yeah. I'm sorry, I got really confused about the numbers because I was looking that we have 186 students in a class. I like record number, but I was wrong. It's not that much. It's 121. 121. Okay. I got the permission from my wife so that I can still have my in-class quizzes, but I cannot promise you anything else because I have already lost you a coffee. You know, the rector is not saying hello to me anymore. I don't know. You know, I'm kind of running out of the idea. So I can just take a look at the scoring and that's it. So let's see. What do you think is going to be the success rate today? How much? It's not going to be 100. So we know that it's not going to be 100. But how much? How 90? Look at this. So 120. Is it this? Okay. Is it just me or is this a record number? 130 answers. I think it is a record number. Okay. With this record number, we're gonna score 100% like this, just like this. Okay. Now, 11% of you, please join the WhatsApp group because WhatsApp seems to make a sense. So how you can join into WhatsApp? Okay. Take yourself in a first lecture of this year. There's a QR code in the first slide. Take a picture of that, join in. And the 161 members. Something is off. I think we need to simplify the communication, I think. And I heard, this is what I heard. I don't know maybe if I should follow this or not, but I heard that Heikki Handels, the guy behind of the semi-empirical approach, is also having the class quizzes in his class. He's saying that if you give an attempt, you're going to get the points. Doesn't matter if you score it right or wrong. So should we do it this way too? I don't know. I guess it is more fun this way. What do you say? Yeah, it's more fun this way. Okay. Okay, so let's continue the story about the direction valves. Um, sorry. You always need to go this order, so I need to first solve this, and then this. But not right now. One more time. And is it still okay? So online participants can see this? Yep, here it is. Very good. Okay, actual equations depends on the what is that you're connecting. You know, what is the actual operation configuration of your direction valve? So this is not that far from the throttle valve we looked at a little while ago. The difference is that now the flow changes as a function of spool position and the pressure difference. So there are two components instead of one. So in a valve that there is no moving components, it's just the pressure difference that makes a difference. Here is a pressure difference and spool position. And again, we're going to use this sine function to make sure that the pressure can travel both directions. Okay, so if it is a spool position that is a positive, then what is connected is a pressure and A. Pressure is this one, A is this one. As the spool moving this direction, they are connected here. This is how they're connected. B is connected correspondingly to tank. So that's how it goes. These are the equations that describes that particular configuration. Then we are assuming that there's a zero land. When the signal, no, let me correct myself. When the spool position is zero, then we are assuming that there's no flow rate whatsoever, so no moving components whatsoever. When it is negative, when it is moving this direction, then it's going to be A that is connected to tank here, and then B that is connected to pressure source. That's how it goes. All right. Digital, yes, sir. Oh my God, a fantastic number. Fantastic question because, what's this one? How much is this? This typically is describing its scale to the control signal that the valve can take in. So typical values are, because usually the valves are controlled at plus minus 10 in voltages. So usual numbers are plus minus 10. 10 is corresponding full opening, minus 10 is full opening, but the other direction. 0 is going to be the position in the middle. So that's the usual number. But that depends on the valve you're dealing with. So if I'm going to jump this example, this is an example that I'm about to show you. Let's take a look at that. And let's get back to digital hydraulics momentarily. So here is a direction valve, and the manufacturers are giving me the properties that this is a direction valve where this shows a relationship between the valve opening. Look at this number. This is 10. This is voltages minus 10 to 10. Again, it ranges from one manufacturer to another, but it says that in nominal flow with the full opening is going to be 24 liters per minute when the pressure difference is 35 bars. So it tells me the information that the size of the volume or size of the valve when I'm here can be computed. Use it. This equation we looked a little while ago. We actually looked this equation that Q is equal than the CV multiplied by fully opening and then the pressure difference. This is a pressure difference. This goes here. Then liters per minute is going to be this guy here. It's going to be this one here. And then this is going to be 10 because this number. You can, okay, sorry, this is super small. Let me see if I can. No, I cannot make it any bigger, but this is minus 10 to the 10. Yeah, you just cannot see it. You need to take a look at this from the YouTube because in YouTube it's more clear than it is here. But I can tell you that this x-axis here ranges from minus 10 to 10. Okay, so 10 is here, which corresponds to fully opening. So the opening is 100%. It is mentioned here with a fully opening. So that's where I'm able to get this U value. It's corresponding to 10. Okay, now this is going to give me the semi-empirical parameter. So again, here is my flow rate true. This is my full opening, 10. And this is going to be my pressure difference. Look at the units. So it's getting even worse. Again, you can convert your units, but not recommended to do so. So this was the first part. Second part, what about the time constant? This is a Bode diagram. Bode diagram is made in a way that you're sending the signal to your direction valve. And the signal is something that is functioning as a function of time. So this is a signal in such the way that it comes with a low frequency, with a fully opening, fully closing, like 10 minus 10. 10 minus 10. And then when the time is evolving, you increase in the frequency. You're making these up and downs to be more closer to each other. So the frequency started to increase. Like this. You're able to follow my drawing, which is not the highest possible quality, but you understand what I'm trying to say here. In some point, the signal can do it really, really rapidly. No limitation, but the spool cannot. You understand that if the frequency becomes to be extremely high, in certain points the spool is saying, this is it. I had enough. I'm off the game. When it's off the game, it's getting confused because the signal is controversial corresponding its actual position. And this is where we can see how fast is this valve. Where exactly we see this? Well, this is a Bode diagram. This shows what's the difference between the signal and actual position. Team Finland, I'm very sorry about this again because this is with the very small font. You don't see this, but let me read it to you. This says 10 hertz. This says 20 hertz. This says 40 hertz. This says 50 and so on and so forth. So this is a frequency. When you keep on increasing the frequency of input signal, this shows how much is going to be the difference between the actual spool position and the signal. And when you have a fully opening, fully closing, like absolute max min all the time. And then when you look at that, when this difference becomes to be 45 degrees, so it's roughly somewhere here, that's when the difference becomes to be too much. That's the limit of this particular valve. Of course, if you're not having the full opening, full closing, if you're moving like this, is corresponding to another curve, which is a 5% opening, closing. That is faster, of course, because you don't need to move that fast. But this is what we're considering is a speed limit, movement limit of this particular spool, this particular valve. So I'm going to take this number here, which is 35 hertz. It's going to give me the time constant. And my final equation describing this direction valve is going to be, where is it? Rest is left for reader's exercise. I don't know if you can see this every now and then, but every now and then when there's really the climax in the textbooks, when you're really getting excited, that finally something concrete is about to happen, then it comes this statement that kills everything. Rest is left for reader's assignment. You're like, come on. Just when you were excited about this thing. Here's the same thing. Rest is left for your assignment. I'm going to give it to you next week. But these are the parameters needed to create this equation, and then that's it. Okay, let me put this on. Let me explain a little bit about the digital hydraulics. And then we are going to have the next in-class quiz. Now, you recognize that the conventional hydraulics is all about how to move this spool back and forth. So it's based on the spool that is closing and connecting boards differently. And they can be moved mechanically by the stick, or more often they can be moved by magnets, or they can be moved by pilot drives and so on and so forth. There's many different opportunities, but there's still like moving components that can have multiple different locations, like infinite number of locations to be specific. Now there's an idea that what if instead having this kind of like analogical position that can move back and forth, take any position you want, we have a little bit of different concept. What if we're going to have on-off valves, many of them, each of them can be having different sizes, and these on-off valves can be either closed or fully open, but nothing between. On-off valves, like the title implies. And having multiple of on-off valves, you can have kind of the same idea than this continuous motion of the spool in a direction valve. So what about this? Again, it works like the way that you have, like these are these on-off valves. Each of them can have a different values, and combination of them gives you the different, like almost like different steps. More the valves you have, the smaller the differences between the steps. This is called digital hydraulics, and we're going to take a look at the animations about the digital hydraulics momentarily. But what's the big benefit? Is it is still based on the pressure losses? Yes, it is still based on the pressure losses, but they say that there is a zero leakage. I don't know if it is really a true statement, because I just explained that whenever there's a hydraulics, there is always a leakage. You cannot get rid of the leakage, but they say there is a zero leakage. There is less power losses. Yeah, maybe, but it really depends how you're designing your pump. And here comes the beauty of digital hydraulics, because you can take a digitalization all the way to the pump. And a pump which we haven't touched yet is like typically a piston pump. And then when the piston is moving back and forth, you can make a decision in every stroke whether or not you're going to put the energy to your system or not. You can kind of have it move without any pressurizing at all. Or if you have a signal somewhere in your system that I actually need a little bit of more energy, then you can act like need basis. Okay, energy is needed, here is your energy that you needed. And this kind of combination seems to have a lot of promises, because now you can actually work in a way that the energy that is leaving from the pump is traveling all the way to your actuators with minimum amount of pressure losses. Why this is great? Because the pressure losses is also the energy losses. So then you have the highest possible energy efficiency. Or let's say that you can enhance your energy efficiency by using this kind of digital hydraulics. So the valve itself, yeah, okay. They said that the promise is a zero leakage, accurate control. Yeah, I can believe that, but I don't see that as a big benefit. But the big benefit today, when we are very concerned about energy consumption, is that it allows you to optimize your energy consumption. That seems to make quite a bit of sense. And they say that the drawback is related to there is a complicated algorithms. For sure, it's a complicated algorithms. If you take this all the way to the pump, this is going to be something that is no longer a very simple system. But let's see if we can take a look at the YouTube animation, YouTube video about the digital hydraulics. Can you guys still see this? Okay, let's see if this works. Not good. Oh yeah, this can help. Still no.
All valve functions, such as pressure.
Okay, you need to be very, very quiet because otherwise you're not going to hear
Hydraulic
this.
system, which has many different types of valves.
This is not existing. This is my headset. It's not going to help you too much.
Sizes.
Okay, let me take it in the back.
Hydraulics, the system variables, pressure and flow, are controlled with multiple on-off directional seat valves. Each valve is solenoid operated and has only two possible positions, on and off. This is why the term digital is used. These valves are used to implement all valve functions, such as pressure, flow, and directional control. Contrary to a traditional hydraulic system, which has many different types of valves, a digital hydraulic system has a large number of only on-off valves. By connecting in parallel three on-off valves of different sizes, such as 1, 2, and 4, 7 different flow quantities can be achieved. 5 on-off valves can achieve the control resolution of a traditional proportional valve. A group of on-off valves in parallel make up a digital flow control unit, called DFCU. At least 4 of these units are needed to substitute a proportional valve in a hydraulic circuit. Each DFCU is used to control one of the 4 control edges. The main benefit of digital hydraulics is the ability to control each control edge independently. This reduces power loss and enables precise control. Additionally, seat valves have zero leakage, as opposed to the high leakage of proportional valves. However, the challenge with digital hydraulics is the complexity of the control algorithm. Each valve needs to be controlled individually, and this results in large numbers of valve position combinations, although each valve has only 2 possible positions.
Okay, I misunderstood this thing. So I said you incorrectly earlier. Oh, no, no, no. That's enough. That's enough. Hmm. Uh, no more. This one. I said this incorrectly because where is that I am now? I said that here. I said that there is a zero leakage. I okay. Okay. Zero leakage here is not referring to oil coming out from the system, but this is a leakage that happens over the land of the spool. So, when the spool is having the zero land, I said that there is a leakage, that the pressure channel is connected to A and B, or let's say A, and that and B possibly too. This kind of the leakage is not a problem when you have this digital on-off valves. But I think, honestly, like I said earlier, I feel that the biggest promise is related to if you're able to connect this all the way to to pump and make a decision case by case, whether you need the energy in your system or not, then it's almost like, this very, very classical solution that you have pump that is directly connected to your actuator. This is where the energy efficiency is the highest possible, and which is really, really hard to do in a real life application like mobile machinery. But this becomes to be close to it. Okay. Complicated algorithm was a problem, so we learned that. Okay. And then, where is that we are now? My in-class quiz, second in-class quiz, which is going to be the last one today, is going to be digital direction valve consists of spool controlled by computer. Spool by computer. Number of on-off valves. Spools controlled by magnet. Spool that moves incrementally. This is going to be simple. We're going to score 110% today, right? Because it's so simple question that I think that you're going to score 100% anyways. So I think, yeah, let's make it up. Let's make it open. Okay, so it's going to be, you don't see it right now, but you're going to see that momentarily. So it was, not this Toyota. I don't want to see this Toyota stuff, but this one, Socrative, and we're going to move on to next one. Digital direction valve consists of spool controlled by computer, number of on-off valves, spool controlled by magnets, spool that moves incrementally. Okay. WhatsApp community is saying B. Is it again? Is it like if I would join in the WhatsApp community, I can vote as well? Can I? I would. Okay, we'll do that. We'll do it. And I also gotta make a comment like, "Oh my God, this is the best course ever." Is the officer allowing to give a comments to? Yes. Fantastic. Okay. So what we're going to do today is that once we are done with this in-class quiz, we're going to go back home. We continue next week. Next week, we still have a few things to cover, including the hydraulic cylinder and the famous stick-slip friction, which is a common knowledge in engineering. You need to be aware of that thing because it happens all over. And it's like this. Okay, you hear this noise? You hear the noise? Where the noise is coming from? Stick-slip friction. How that happens in reality, I'm going to explain that to you next week. But we're still missing like 30 answers in this in-class quiz. So once we're done, then we're going to go home. I got flat tire this morning when I was biking to university, so it wasn't the best possible start for a week. Not cool. Not cool. All right, so we got 109 answers. 110, so momentarily we're able to close it. And like mentioned, next week we're going to continue with the rest of the stuff about hydraulics. Then still, I'm not sure, but I think I'm going to explain something about the flexible bodies. What it means if you have a deformable bodies, how you can take that into account. Yeah, I'm not going to take you all the way to the final Tillman method, but I'm going to give you a little bit of, what it means if it is a deformable body. What are the different categories in deformation? Okay, I think it is going to be something you guys going to like a lot because a few years back, we got the complaints from student union that professors are not explaining what exactly they do in their research. So what we do, one of the big disciplines we do in our research is related to flexible multi-body dynamics. So now if you're going to solve for next week, this is what you ask for. No, I'm going to keep it in a level that is going to be very enjoyable. Okay, 126. So in class quiz, the success rate is going to be 95. 95. So one more answer and we are good to close this one. So it's 95. Look at the size of my brains. Okay, guys, take it easy. See you next week.